This is not just bad weather. It is a catastrophic design failure unfolding on the modern front lines in 2026. The Sweden BvS10 Arthur is proving an outrageous tactical paradox, operating as the ultimate artillery hunter in deep mud, while multi-million-dollar wheeled systems from the United States and Germany are rendered completely useless. When the treacherous spring terrain turns Eastern Europe into an inescapable swamp, heavy combat vehicles sink rapidly under their own weight, transforming into defenseless targets for precision loitering munitions. Leading global defense analysts argue that, on paper, the only tactical salvation for radar crews would be an immediate deployment of specialized subarctic mechanical engineering. How can a massive 8.5-ton armored vehicle comfortably hunt down hostile batteries while gliding over lethal bogs with a ground pressure lighter than a human footprint? The stakes on this high-tech battlefield are absolute. When a conventional counter-battery radar activates its passive electronically scanned array, it has a mere 90 seconds before hostile electronic tracking systems calculate its position and deploy counter-strikes. For wheeled platforms carrying systems like the ANT-37, which generate a crushing ground pressure of over 2.5 kilograms per square centimeter, escaping through wet soil is physically impossible, leaving the expensive equipment exposed and highly vulnerable. By contrast, the Sweden BvS10 Arthur utilizes an articulated dual-cabin design and wide rubber tracks to redistribute its entire mass, dropping its ground pressure to an astonishing 0.3 kilograms per square centimeter. This allows the system to actively track over 100 targets per minute, feed precision coordinates to friendly Archer artillery, and slip away into the tree line before the first hostile shell impacts. Before we go on, what would you choose in this situation? Raw numbers or maximum mobility? Subscribe to the channel right now to stay updated on global defense tech. And tell me where you are watching from. To understand why the tactical situation has become so critical in 2026, we must look at the brutal physics governing the 90-second countdown of death on the modern battlefield. Counter-battery operations have shifted from a game of chance to a highly automated race against destruction. When a standard mobile radar array fires its electromagnetic beams to detect incoming artillery trajectories, it immediately turns into a giant radio beacon on hostile electronic warfare monitors. Western defense reports tracking conflict data from 2024 through 2025 reveal that once a radar emission is detected, the opposing side requires only 90 to 120 seconds to launch a deadly response using precision-guided shells or rapid loitering munitions. This extremely narrow window means that a radar platform must possess the ability to perform shoot and scoot tactics, meaning it must pack up and accelerate away from its broadcast location within 1 minute of operation. However, heavy wheeled transport trucks carrying older systems like the ANT-36 are facing physical limits. These vehicles distribute their immense weight over standard rubber tires, creating a high ground pressure of approximately 2.5 kilograms per square centimeter. When the severe seasonal mud of Eastern Europe lowers the load-bearing capacity of the soil to less than 0.5 kilograms per square centimeter, these heavy trucks sink instantly into the terrain. Open-source intelligence databases indicate that more than 40% of expensive Western radar systems lost during recent campaigns were not destroyed by mechanical failure, but were caught completely defenseless and immobilized under the deep mud. A multi-million-dollar sensor suite becomes utterly useless the moment its wheels lose traction. This glaring physical vulnerability has left military planners looking for an immediate mechanical solution to prevent their critical surveillance assets from becoming sitting ducks in the mud. The engineering solution to this critical mobility crisis comes from the subarctic design philosophy of Sweden. The BvS10 Armored Articulated Track Vehicle successfully resolves the physical limitations of soft terrain through a radical mechanical layout. Despite weighing 8.5 metric tons, the vehicle distributes its entire mass across extra-wide rubber tracks molded over a synchronized dual-cabin system. This configuration drops the ground pressure to an astonishing 0.3 kilograms per square centimeter, which is significantly lighter than the average adult human footprint of 0.4 kilograms per square centimeter. A heavy-duty hydraulic steering joint connects the front and rear cabins, allowing the vehicle to continuously push traction forward and glide effortlessly over deep mud that completely immobilizes standard wheeled platforms. Mounted on the rear cabin of this supreme cross-country platform is the Arthur Mod D artillery hunting radar developed by Saab Surveillance. This passive electronically scanned array operating in the C-band represents the pinnacle of modern electronic tracking. The system possesses the mathematical computing capability to monitor more than 100 projectile trajectories simultaneously per minute. It can detect and track incoming 120mm mortar rounds from 55 kilometers away and larger 155mm artillery shells or multiple launch rocket systems from a distance of 60 to 100 kilometers. By calculating the exact reverse ballistic arc, the radar pinpoints the hostile firing origin with a circular error probable of less than 0.15% of the total range. Under the ongoing Joint Collaborative All-Terrain Vehicle Program, which is delivering 663 new BvS10 units through 2026, these systems are redefining front-line defense. Combined with the automated Archer mobile artillery, the BvS10 Arthur can detect a hostile threat, transmit targeting data, and displace into dense forest cover well within 60 seconds, easily beating the 90-second destruction window. Yet, even the most advanced subarctic engineering contains its own glaring vulnerabilities. The unique articulated structure of the Sweden BvS10 Arthur relies completely on a central hydraulic steering joint. Defense logistics experts note that if this specific mechanical intersection is damaged by flying shrapnel or suffers from heavy fluid leakage due to friction in extreme environmental mud, the entire 8.5-ton vehicle immediately loses its steering capability, turning a $4.5 million to $6.5 million asset into a defenseless target. Furthermore, the massive electromagnetic signature emitted by the powerful C-band radar creates a permanent risk. Even if the vehicle can physically escape through thick, wet soil, the moment it transmits waves to track targets, it flashes like a radio beacon on enemy surveillance monitors, inviting immediate saturation attacks. This technological reality leaves military strategists in 2026 facing a critical doctrinal dilemma. Armies must choose between purchasing large numbers of cheaper, standardized wheeled radar systems that risk total immobilization in harsh seasonal mud, or investing heavily in the expensive, high-maintenance luxury of Swedish articulated track technology to guarantee survival. The ultimate lesson of modern counter-battery operations is clear. Cutting-edge surveillance software is completely useless if the mechanical hardware cannot physically move to its next tactical destination. Survival on the modern front line requires a perfect balance between sensor performance and raw all-terrain mobility. If you were a defense procurement official tasked with preparing a military force for severe weather campaigns, would you prioritize buying a larger fleet of economical wheeled platforms, or gambling your entire budget on a smaller number of highly specialized, expensive dual-cabin tracked vehicles? Drop your thoughts in the comments section below, hit that like button, and subscribe to the channel for more deep analytical defense updates.